they could have been silent. Okay, I don't want to speak out because it's difficult for me. I'm a climate scientist, but if Koonin does it, it's good. But that's not what they do. They oppose you.
Right? Yes, they do. But again, I'm a scientist, and if they say Koonin is cherry picked, for example, as they do, show me exactly where. All right. There was somebody said to me this morning, well, you cherry picked the precipitation, the heavy precipitation data in the book. There's a discussion of heavy precipitation in the book. And so I said, exactly what? And they said, well, you only focused on the US. So there's a graph that shows the US. But then I quote the IPCC at that time that says, we can't say much about the rest of the world because the records aren't very good. There's some positive trends and negative trends and so on. So I think I did accurately represent the IPCC statement at the time. Things have changed a little bit since, but I'd hardly be accused of cherry picking.
More generally about science itself, indeed, the data in the US are not data for the whole world, but they have the advantage to be about a quite big part of the world, and also, big as possible, and also with the good records. Good records.
We're looking for, the US is only a few percent of the globe's area. I don't know what it is. So it's not very representative of the globe as a whole. But the advantage is that we have dense coverage in terms of area, and we have pretty long time records of a century or more over much of the continental US. And people should remember that we're looking for small shifts over decades in temperature and precipitation, clouds, winds, and so on, extreme events. And so it's very important to have precise long-term records.
And a part of the data, another important focus in your book is about models, modeling. You're smiling. Indeed, that was your first.
This is my first love. Not so much for climate, but in other fields first, and it's I do know it well.
So, could you explain to us what is a model, scientifically speaking, and then in climate science, and what we can do with them, and especially what we cannot do with them?
So the most advanced models, it's easy to make a model with pencil and paper, right? But that's not what we're talking about. We're talking about massive computer models that cut the atmosphere and the ocean over the whole Earth into boxes. Some number of boxes going up into the atmosphere, some number of boxes going down into the ocean. And those boxes today are about 100 kilometers on a side. And the computer models, will follow the flow of matter, of energy, of momentum, radiation, water vapor, and so on, through the boxes, step by step, typically about 10 minutes per step. And then to describe the pattern of winds and clouds and rain and so on over the whole Earth. This is the best we can do, but there are several problems with that approach. You'd like to make the boxes as small as possible, but as I said, they're about 100 kilometers on a side. That means that there are many phenomena in the ocean, or more easily understood in the atmosphere, that happen on smaller scales than 100 kilometers. Clouds are the most obvious example. But if you only got one number that describes the temperature and humidity and wind in a box, you have to say how many clouds are there, where are they, and so on. And there's no rule for doing that is universally accepted. Different modelers make different assumptions about these subgrid phenomena, things that happen on full scales. And because we're looking for small shifts, you get very different answers from the different models. So the UN, the IPCC, uses a collection of about 40 different models produced by different groups around the world. They don't agree with each other, and most of them don't agree very well with the data, and it simply averages over them. that gives me a little bit of pause since we're talking about making trillion-dollar decisions on the basis of these models.
So how can it be that so many people believe in models, even if most models are not in agreement with each other? How can serious scientists say, okay, we have plenty of bad things, let's average them and that will produce a good thing?
The serious scientists don't say that. They understand the limitations of these things, and the people who build the models understand it as well. It's just that they get co-opted, corrupted, the results, when you get to the scientists who talk to the public. And the model says, the science is settled. We've got to make drastic changes and things. It's just not like that. Maybe we should make drastic changes, but there's a lot of room to say, hey, wait a second, let's make sure we've got a better understanding.
And what is interesting in climate is that we always, we can talk about models, we never talk about theory. So there is no general theory of climate. And could it be that someday we get one that would help to get a...
No, I don't think we'll ever see a theory of climate. You can build simple pencil and paper models, as I do for my class, and most people who teach climate do, that kind of illustrate the basic principles, get the order of magnitude of energy balance right, can understand convection and the general pattern of the winds. But we are looking for 1% shifts in a complicated system for which we have poor historical data. And you can't build a theory for that. It's like trying to build a theory for biology or for the human body. It's just too complicated, too many details matter.
So you think it will never exist?
Well, you can't say never, but it's hard to see how that's the case. Just give you one example. A very important part of the climate system is turbulence and the complicated swirling of either the atmosphere or the ocean. Turbulence was a phenomena that was known in the 19th century and was never solved as a theory in the 19th century. As one of my colleagues likes to say, it's the one problem in 19th century physics that's still with us in the 21st century as a theoretical problem. And so, unless you've got a theory of turbulence, you're not going to have a theory of climate.
And how about, as a physicist, can we reply or study the idea that we have 1.3 degrees, not a big deal right now, but if we get 1 degree more, then we will. There is a threshold, a tipping point after which things won't be manageable at all.
So this is always the threat that people say. Economically, there have been analyses of tipping points. There's one paper that was published in the Proceedings of the National Academy of Sciences in 2021, I think. They looked at 8 different tipping points. So methane outgassing from the Arctic, from the permafrost, the Atlantic circulation slowing down, the Amazon burning up, and so on. And they tried to analyze the economic impact of these. And it's a few percent more than the few percent already that was in the... So again, limited global impact, local impact of course, but not certainly the end of the world. Also, it's very hard to find such tipping points in the historical or geological record. Yes, there have been climate shifts, but apart from unusual circumstances like the Younger Dryas, the climate unfolds over decades or centuries, and we would have time to manage them.
So you mean that tipping points are not what they used to be?
Well, no, that's a good way of phrasing it. But again, if I'm sitting in a developing country and you say, you can't do that because there might be a tipping point out there, I don't think that's a very convincing argument.